Ladies and gentlemen, welcome to the Research Center of Fraunhofer IFAM in Stade. My name is Urs Römer. I'm a group manager at the Department for Automation and Production Technology here at Fraunhofer. We are here in the CFK North Research Center. My colleagues and I have been working here in the broad field of automation with a focus on the aviation industry for more than 10 years. Since the COVID-19 pandemic is running, our daily business has changed a lot. Instead of our booth at the ILA 2020, we would like to invite you today to a small tour through our research lab and show you 3 outstanding examples of our R&D work of the past years. To give you an idea of how aviation production in the 21st century could look like. Automation has become an ever-present topic in the aviation industry in the last years. A new aircraft not only has to be climate-friendly and quiet, it should also be possible to manufacture it in a larger numbers, at lower costs and in less time. This triangle demands a lot. Not only the OEMs and Tier 1 supplier have to adapt these requirements, the entire supplier industry has to go through a change. Perhaps some of you now asking, why do I need such a research center? Here we can offer our industrial partners the environment to develop and test new technologies in a full scale together before they were implemented in daily production at your customer's site. In the next 25 minutes, my colleagues will give you insights into the latest fascinating topics Fraunhofer IFAM is working on. These film episodes were recorded previously. Meanwhile, you can type your questions in a live chat option here on the right side. Afterwards, my colleagues and I will answer some of these questions in a roundtable discussion. And now we will start with my dear colleague Pat Raval, who will show you how a lightweight robot can be used in an assembly situation.
Clean Sky ACCLAIM is a European project which started in the year 2017 and aims for a planned completion by the beginning of 2021. The acronym ACCLAIM stands for Automated Cabin and Cargo Lining and Hatrack Installation Method. As the name suggests, the project aims to automate the cabin and cargo assembly processes for new lining and hatrack parts. The project work also includes the use of augmented reality for easy installation and process monitoring. The project comprises altogether of 4 projects, which are Calito for the design of new parts, Eureka for the automated installation of these parts, Sympha for the virtual planning, and Vista for the final quality assurance. Out of these projects, Calito, Eureka and Sympha have been completed successfully in the month of January this year. Let us go through some of the results of the projects. So we are currently standing in the cabin floor area just in front of the fuselage. This area is the entry point for the automated logistics systems. The robots and the parts are loaded on an AGV and transported by an industrial lift. With the help of local sensors and global communication systems, they are guided autonomously through the door opening into the fuselage. The robots and AGVs are designed to stay within the limits of the maximum load capacity of the floor. Let us go through the cabin area and have a look at the parts. Here you can see the side panels designed for the project. It weighs about 7 kilograms, which is still 10% lighter than the current side panels in the aircraft industry. With the help of the lightweight robot, they are mounted to the structure. At the back of the panel, there are several fixtures which get completely attached to the counterparts on the structure. The fixtures are designed in such a way that they can compensate for a few millimeters of robot inaccuracies. Also, its manual installation is faster due to smart fixtures and it takes only a few seconds. So let us have a try here. This is the side panel. The first step is to put them onto the rails. And then just have a slight push. And in this way it's attached, and closing the flap will completely lock it. The hatrack is more than 2 meters long and weighs about 42 kilograms, but they are still lighter than the current hatracks in the aircraft industry. An empowering arm is used for automated and semi-automated assemblies of hatracks. At first, these tie rods are brought into these hooks And then the part is rotated such as to get a completely locked assembly with the fuselage. In order to guide the worker with proper assembly instructions, a HoloLens is used. In the project, a total of 4 side panels and 2 head racks were installed. Now that we have had a look into the cabin area, let us go through the cargo area. So this is the cargo area, and the distance between the floor and the ceiling is hardly 1 meter. The space here is also very confined and not favorable for walking continuously for hours. The ergonomy analysis of different processes involving workers inside the fuselage did not portray a positive picture, especially here in the cargo area. Hence, just like the side panels in the cabin, the panels in the cargo area were also installed automatically with the help of robots. To summarize the achievements of the entire project, let us go through the short video.
In the Clean Sky 2 ACCLAIM project, new installation techniques were developed and validated to optimize the lining installation processes for airplanes. The focus of the project lies on an automated assembly, human-robot collaboration, as well as newly designed aircraft parts and a mock-up fuselage section which are ready for automation. An automated guided vehicle, short AGV, identifies the carrier type through a QR code. After aligning, it automatically docks itself to the carrier. AGV and lift communicate with each other and exchange location and floor data in order to take the load to the desired lining area. The AGV and the part carriers are designed to meet requirements of limited access and load capacity inside the aircraft. An integrated vision system scans the side panel and identifies the best position for gripping and assembly. The panel itself is held by self-locking fixtures on the fuselage structure. A digital twin with a dashboard software enables monitoring of the whole process from a remote workstation. For the assembly of the hat rack, the robot assists the worker by lifting and installing the heavy load. The instructions for the correct assembly are provided to the worker by a HoloLens using augmented reality. The robots are designed to operate even in the cargo section of the aircraft. This can avoid the ergonomically unfavorable postures of the workers in the confined area. The vision system identifies the gripping position, and the trajectory is planned to avoid all possible collisions in the confined cargo space. The validation of the processes yielded positive results in terms of productivity, ergonomics, and costs. The developed solution is a potential alternative to conventional assembly methods for future aircraft cabin and cargo installation.
The entire work of the research project was divided into different work packages. The project Calito was undertaken to design and develop smart, lightweight components for an easy assembly. The automated logistics and installation of components was a part of Eureka project. Ergonomy analysis, digital twin, and augmented reality were a part of Sinfal research project. The mock-up fuselage was built by Fraunhofer for validation of these projects. The project Vista, which is still ongoing, is related to automated quality testing of aircraft interiors. The installed components will be inspected for defects such as gap, steps, misalignment, scratches based on color and textures. This will result in a better quality assurance and will ease the process of generating quality reports online. Vista is scheduled to be completed in January 2021. Upon validation, this will be finally integrated into the results of the project ACCLAIM. The results of these projects are very important for future aircraft industry. Automation of cabin and cargo installation is a major topic for aircraft manufacturers like Airbus, who want to reduce process time and effort. There are still some challenges related to these topics. The development from ACCLAIM project have to be transferred from research level to industry level, where process stability and robustness must be guaranteed. That's so far from ACCLAIM project. If you can have a look at the area behind me, you can see some mobile robots which are used for machining of large aerospace parts. My colleague Christoph Brillinger will guide you through some of the applications.
I want to show you today our mobile machining system that we have created in the project MB-Fast 18. Conventional machines are usually built as a gantry machine. And as you can imagine, if you want to machine a really large component, you need a really large gantry to cover this up. So this is a really big drawback of those. And also they need cost-intensive, high payload foundations and have a high ratio of non-productive time, since a lot of alignment processes and measurement processes are performed. So in this time they're standing still. Our mobile machining center is composed of a mobile platform, industrial robot and a portable CNC machine. The concept behind it is to attach the CNC machine onto the component, and so stepwise fulfilling the machining job, section by section. The big benefit of this concept is that you are able to use several mobile machining systems in parallel. So if you have a medium-sized component, for instance, you use 1 or 2 machining systems. Or if you have a really large system, you scale up and have 3 or 4 systems. So you're really flexible and can use your machines on demand, and you get rid of those non-productive times when you align your component and you're waiting with your machine. So this is a major benefit of being more efficient. We also mobilized a laser tracker for obtaining a higher utilization rate of this measurement system. In the following, I want to show you a short video of the system so you can see it's moving and get a better impression of its functionalities and how it's working.
Within the R&D project MB-Fast 18, multiple innovative companies joined together to actively shape the production of the future. They developed a mobile, self-control production system, AGV, to flexibilize the manufacturing of tomorrow.
While today's machining centers are tied down to one location, our system has been mobilized. This allows us to adapt to new approaches.
This project deals with the fabrication of large structures like they're used in the aircraft industry. Currently, those are machined by machining centers that are just as big as the parts themselves and therefore easily reach lengths of up to 30 meters. These machines shall be superseded to reduce costs and space requirements.
By reducing the size of the machine tool itself, it's possible to mobilize it and to drive to the operating site directly.
In the following, this will be shown exemplarily in a drilling process of an aircraft vertical tailplane.
FFT Produktionssysteme has developed and built up the AGV. We also integrated all developed technologies into one central control.
Because of the omnidirectional drives, the autonomous and wireless system is able to move and navigate completely free inside the production facility. The start of the process is controlled through a high-level manufacturing execution system, MES, or manually from an operating console. For localization of the AGV, a laser scanner is utilized that captures the contour of the surrounding environment.
To calculate the AGV position, we align the LiDAR data with a digital map of the area. The whole navigation is completely autonomous. We enable this by an algorithm that provides the optimal path to any destination within the workspace.
All sides of the AGV are equipped with additional safety scanners to identify people and obstacles. If any obstacle is detected alongside the desired path, the central control automatically calculates a new route to bypass the obstruction. If any person is entering the safety area around the AGV nevertheless, the safety scanners from SICK ensure a safe stop of the vehicle. The mobile platform is reaching its final destination. To obtain a safe and solid stand, rigid feet are extended to lift the whole AGV off the ground. The measuring system also has been mobilized to further enhance its capacity. This provides an ideal starting position for upcoming referencing and drilling operations. The milling drilling unit, named Mobile Block, is now set up in a pre-position.
For determining the position of the robot precisely and meeting highest manufacturing tolerances, a laser tracker is utilized. The robot uses this information to set up the mobile block onto the component precisely.
The mobile block provides workspace for up to half a square meter and the possibility to drill and mill CFRP structures in 5D applications. To determine the exact drilling hole positions, local scanning of the surface is performed. By comparing the scan data and the virtual workpiece in the self-developed software of BCT, the corresponding data and final drilling positions are calculated and transmitted to the machine. The automation of the referencing, job generation and milling application reduces the cycle time of manual processes significantly and ensures consistent quality all over the process. By relocating the mobile block on the part, a flexible extension of the workspace is obtained. At this point, the whole referencing and drilling process starts again.
Within this public-funded R&D project, the production system has shown potential for further applications. It is possible to assemble, handle, seal aircraft components or large structural parts like they are used in the wind or train vehicle industry.
This system has been validated on real parts in 1:1 scale. This demonstrator and the innovative research group allows the active participation and development of the factory of the future.
As you have seen, there was a strong group of partners behind MBFast 18 that has worked close together with us for achieving this goal of a mobile machining system. In governmental funded projects like MBFast 18 was, we are forming groups of partners from the industry as well as from the universities that work with us on those topics. On our YouTube channel you will find more examples of our projects and also on other mobile machining systems, and I really can recommend you to have a look on this channel. On the next stage, my dear colleague Björn Reichel will show you an example of a project out of the field of the automated assembly systems.
Automation in aircraft manufacturing opens up many possibilities, but also poses a number of challenges which we are taking together with our research partners. At first, the handling and positioning of large structural components with dimensions of several meters should be mentioned here. Manufacturing tolerances of unique composite components, process force impact, positioning errors of industrial robots and the tool center points contradicts the high required accuracy in aviation. To achieve this accuracy of sometimes 1/10 of a length up to 20 meters, strategies to reference the parts to one another and to the robot systems, in the assembly area are necessary. With the system reference to each other and a continuous comparison of the target and the actual position, tolerances can be compensated within the process. However, due to the high effort, frequent use of measuring technologies should be avoided. Furthermore, the handling of large flexible components is often not feasible with only one industrial robot and is far too imprecise in positioning. Collaborative application of 2 or more robots can remedy this, but require corresponding further developments in the positioning processes in order to compensate for the robot-related inaccuracy. Another way to enable automated manufacturing of large components is to detect inaccuracies and compensate the tolerances before assembly. Components jigs, which are able to adapt to the target geometries, are a proven means of doing. If the shape and position of the components are adjusted to the target, the following process steps can be carried out more reliably and precisely. In the project FR-Roman, the flexible hexapod jig visible next to me was constructed for exactly that applications. In a corresponding configuration, it is possible to pick up fuselage shells up to a size of the A350 family. This enables us to demonstrate highly automated parallel assembly processes. For example, currently ongoing works within the project Multifal as part of Clean Sky 2 aims at methods and processes for the measurement, handling and positioning of 2 pre-integrated A320 thermoplastic shells and the longitudinal welding process. In addition to the development of technologies for assembly of large structural components, many works also gear forward to the Airbus Factory of Tomorrow concept. All the knowledge and result gained in the projects could have a major impact on future aircraft manufacturing. Another project which covers the whole range of challenges in assembly is AutoGlare. In addition to new manufacturing methods and processes, digital transformation is an important element for modern production. Since a few years, the part of digital tool development, such as digital twins, virtual commissioning and the same, is increasing permanently within our projects. The AutoGlare project, presenting before, focused on a highly automated production of fuselage shell elements. The challenge of applying adhesive film in accordance with tolerances and stringer integration into a double curved skin was achieved not least by the virtual process simulation and derivation of path planning for collaborating robots. All the aforementioned projects are representative of a whole range of different projects in the field of automated assembly. The knowledge and results from successfully completed projects are transferred into new technological approaches and form a solid base for further works.
Many thanks to my colleagues for the insight into the completed projects. Now we have seen what kind of cooperation between robots is able to be performed, which possibilities mobile units can offer for the use of robots in an industrial setting. Not only large robots for machining and assembly tasks offer new opportunities here. Even small robots can scale up the range of possible applications in the field of aviation industry. Combined with technology bricks of digitalization and a wide experience in process development and implementation, we can offer here an ideal environment for your R&D task for a production of tomorrow. Let's go to my colleagues now for a question and answer session. We are now live at the Fraunhofer IFAM in Stade for the roundtable discussion. I would like to introduce my dear colleagues to you again. From the left, Padra Wall, Christoph Brillinger and Björn Reichel. While they presented their project results, you have used the opportunity to ask a lot of questions to them. And we will start with the first round. So, Part, one question for you was, the Clean Sky 2 project is a huge European project and ACCLAIM is just a part of it. After this project is finished, what are the next steps for all the technology parts on its way to production?
Yeah, so within the framework of the ACCLAIM project, we have achieved technological research level of 5. So which is that we have been able to demonstrate this in an operational environment, in a research environment. And the next step would be to maybe take one step further, let's say to try it in the operational environment and how efficient it is, what are the results. That would be, according to me, the next step.
Okay, thank you. Christoph, one first question to you. We have seen that the mobile machining system you've shown to us is a very big-sized one. Is it the only mobile option to make the active working part mobile, or there are other opportunities?
We have focused on several approaches for this mobile concepts. You have seen the MB-Fast 18 project and the platform that has come out of it with this CNC machine on the robot. Before this project we had a different approach. We also evaluated how to use a high precision CNC robot on a mobile platform in the project ProZip 2. So you see, those were two approaches for achieving the same goal, having a mobile machining system. Right now we have a project ongoing where we have a look at a mobile holding fixture for large components that is going through a flow line of this process. So you see, we have focused on the same process. We are getting the component after it is produced and have to machine it, and all the steps in between we have arranged in this very flexible way, and we have evaluated several approaches on this topic, and there are some ideas we still have. So it's a broad field.
Thank you. Björn, You have shown us the collaborative work between two big industrial robots. Which role plays small robot systems in your development tasks?
Yeah, it should be clear that it is not possible to handle such a large structural components we usually focused on, and that's why at the first steps we use smaller systems, lightweight robot systems, for supporting the automated processes. And but on the other hand, we also can use such systems for integrating smaller parts into the larger components. Yeah.
You've shown us the results of the finished AutoGlare project. One question for that is that we have seen a lot of technology bricks with very different ranges. Which part of this you see a big chance to go in production in the next years?
Okay. Unfortunately, Airbus considered the glare materials no longer in the A320 family, but we see many possibilities to transfer the technologies we developed in the project into other processes, production processes. For example, the adhesive tape laying process we can also use in other shell production, and also the string integration is a big and further challenge we can bring into further projects.
Okay, thank you. We have seen that in the ACCLAIM project, it's all the processes which are done today manually, or try to bring in an automated setup. What is the robot system so much faster than the worker today, or what are the benefits for an automation of such a process?
Yeah, if the question is if the robotic systems are faster than the human workers, the answer is not yet. We have achieved different success rates for different parts. For example, for hatracks it was difficult since the parts are itself so big, and the tolerances are very minor. That's why it was difficult, but still I see it that one should not compare it to manual versus automatic. When we use the lightweight robots, we also have human-robot collaboration, which we can use. Today, working in the fuselage, there are a lot of ergonomic issues, and there I think we should not just compare with the productivity, but also on the working factors. And there I think one can also use this kind of systems to show that, okay, it's more ergonomic for the workers to work inside the fuselage, and so we have to consider all the factors.
You have shown us the assembly of sidewalls, of the cargo area panels, of the hatracks. Which are other tasks in the final assembly line and cabin integration which are interesting for robotic processes?
Yeah, I think what we have not considered inside the fuselage are also a few parts. For example, the ceiling panel, just on the top. Some other parts such as the passenger service units, or let's say even the floor area. Those can also be considered depending on what the requirement is.
Yeah, thank you, Pat. Christoph, your focus was hardly on the mobilization of processes. One question which came up is what are the strengths and the weaknesses of mobilization from processes?
A very big strength you achieve is the flexibility you are getting, and when it comes to the approaches that we have on these mobile machining systems, that you really get rid of this heavy payload foundations. But systems become complexer, so you need to find good ways how to control them and how to use them. And also
you need to have some knowledge about measurement technology for referencing and such. So these are, the complexity is rising, but your flexibility is also rising. And one major benefit of the concept of having those middle-sized machines that you have seen, you can use more than one. You can use them in parallel. So we have found out in a rough calculation that there could be an optimal of using 2 or 3 machines for a longer component when it comes to process time and your invest.
You say that it's possible to parallelize the processes with a larger number of such a machining system. This brings me to some questions which came up. What is the main difference between a mobile machining system in contrast to the actual existing gantry machines? Is it so easy to say this one is cheaper and this one is precisely, or is the answer difficult?
Yeah, it's a longer, but it's a major difference. So we have seen one difference is the way we have built it. We're using robotic systems. In 2 approaches in MBFast 18, we have used from the shelf robot with a CNC machine, so the accuracy, let's say, comes out of the CNC machine, so it's decoupled from the rest of the system. In the project before, ProZip, we have created a high precision CNC robot that could conduct those processes. So this is a difference. You have not a gantry machine, which comes with different types of stiffnesses and such, but I think this is going to be too detailed. So when you compare, you have a really different kinematic. This is a major difference. And the size of your system. You don't machine your component in one step, but you do it in subsections, and you have to find ways how to do this.
Thank you for the answer. Another question is that we talked in your projects and also in your answers always about the topic of digitalization. So an open question is which influence and which impact have the digitalization of different processes to the whole field of process automation today? Maybe Björn.
I already mentioned it in before, the impact of the digitalization and connecting of plants and so on, increasing much more, and so we have seen it is a good opportunity to use such tools for enable modular processes to get information about the process before we will do it, and we can do the processes much more precisely and reliably. So there's a large impact in our project and our works.
Mm-hmm. In all the projects we have seen here in our technology center that we have very big aircraft components today, where all the projects was dealing with about. Is the work here focused in this field, or there are opportunities for smaller parts or other industries?
Yeah, there are different things. So we also had some topics about logistics, internal logistics here within the last years, but also when it comes to machining, we had some works done in the automotive industry, so smaller sized components that we have machined, also deburring of smaller size. So the technology itself can be used for really large systems, as you've seen with these mobile machines, but you can also use a machining robot for smaller components. So the size is not the limit.
Is the same available for the assembly situations, or by the experiments?
Yeah, for sure. The technologies we have developed are adaptable and can be transferred into other productions. Same as Christoph said, the automotive area is a possible production where we can transfer our results, our gained information in the project, and also I would say it is possible to transfer it to the railroad technologies and building railroad wagons or something like that. Yeah.
All the technologies we've seen, you always talk about different technology levels where the technology is today, and that seems to be the gap between the today's state of art development and the implementation in a production field. Can you describe where normally the field is for the task we've done here in this research center? Maybe part.
Yeah, we have different projects in having different technological readiness level. We have some of them which are very basic, where we just try to find out if it's doable. First of all, if the concept works, that's the first step. Maybe level 2 or 3. But we also have, like in front of the IFAM, we have this big hall where we can do the experiments on 1-to-1 scale. That's the main advantage, and that's why we are trying for the research projects for at least 5, 6, or if we have to even reach the industry environments, we could also go to our customer's place and do some experiments there and have it validated for a higher technological research level.
Thank you. Unfortunately, our time is already over. We are sorry that we wasn't possible to answer all the questions which are asked today in the live chat. But we can answer your questions afterwards. Please use for this the possibility to contact us, use the ELA website, use our personal website to go in contact with us. Feel free to contact us, ask your questions, and maybe we get in an interesting discussion together. Maybe some of your colleagues wasn't possible to take a look at the our live show today. For all of these people and also for yourself, we will post a recording of this event in the next few days and we'll publish it. And we will thank you in conclusion to your attention, for your time today, and we wish you still a nice day, and thank you to all the colleagues here. Goodbye.